So welcome to this session about the Groovy compiler. I hope you're ready after lunch. So, who am I? Maybe some of you already know me. So my name is Cédric Champeau. I'm an Apache Groovy now committer. And I've worked with Groovy pretty intensively for the past maybe 5, 6, maybe more years. And I've contributed some features of the language recently, such as the static compiler, traits, many things around DSLs, basically, because I started as a user building DSLs using Groovy, and I had to improve the performance. I had to do that kind of stuff, so dig into the code, make it better, improve. So all the things that you can do today, you too. So please contribute to Groovy, submit patches, pull requests. We're very happy with that. And now I am working for Gradle on the open source project of the same name. And if you have questions about that, I would be happy to answer that after this talk. So enough talking about me. Just if you want the book, you have a coupon that you can use. There are, I think, 30% off today on all the books on mining using that coupon code. So obviously I would prefer that you buy this book because it's better for my royalties, but yeah. So let's go. So we're going to do a deep dive, but actually the first time I did this talk, it was at Spring 1, and I had 1.5, and I didn't manage to finish all the slides. So the second time in London, I did that in 45 minutes, and I didn't have enough time to finish. So I won't have enough time to finish today either. So it's going to be a deep dive in a small bath, basically. So, first, what is Groovy? Groovy is not an interpreted language. It is a compiled language. So what does it mean to be a compiled language? It means that all you have is processed before it is executed. So you have some languages that are totally interpreted. So you have some phases just to be able to parse the text, and then it executes nothing more. With Groovy, it's basically the same as with Java. It is compiled. And it has its importance, because some people, maybe not today, but it's been for a long time, people told, okay, Groovy is slow because it's a scripting language. And scripts are not compiled, so it's slow. You know, they don't even try to use Groovy. It's slow because it's scripting language. It's totally untrue. And even for you, maybe most of you now do some JavaScript, and JavaScript is a scripting language. But it's pretty fast now, and it's actually pretty impressive how they can improve the performance. And we have techniques to improve the performance. And we're going to talk about those techniques. One of those techniques is having what we call a just-in-time compiler. And a just-in-time compiler is something very smart. Probably, I would say this is probably the best part of the JVM. The just-in-time compiler is something that is capable of interpreting the code that you have, compile as bytecode, and recompile it during the execution of the program so that it's optimized for the specific use case that the program stream is actually seeing. So it's optimizing as the program executes. So Groovy doesn't have to do that, because Groovy lives already on the JVM. So Groovy is a language that lives on the JVM, and because the JVM has some runtime with a just-in-time compiler, we also benefit from that for free. So super cool. So the key for that is that Groovy compiles the scripts, compiles the classes to JVM bytecode. So the same bytecode as what you would have in Java, in Scala, in Clojure, etc., etc. Groovy is not different. So what is the difference between a script and a class? Well, this is a Java class. It has a lot of boilerplate code. We all know that. It's very simple. If you compare that to the Groovy script, in Groovy we just focus on what we need, print line, done, okay? But in the end, this is exactly the same as the previous case. Groovy generates classes. We live on the JVM, and the first class citizen in the JVM is a class. So there is no way in the virtual machine to create something that doesn't have a class. Everything has a class. So basically, classes, Java classes are compiled to bytecode. Scripts are also compiled to bytecode. And what we want to focus on is actually what happens at runtime, not what happens at compile time. So this is the main difference between Java and Groovy. It's not what happens at compile time, because both do something at compile time. Both create bytecode. The difference is what happens at runtime. So let's explore that a bit. Yep. So compile time means I have a set of source files. I'm going to compile them. And in the end, what I get is bytecode. And that bytecode, it's just a stream of bytes. You can store that into a library, into a jar file, into class files. We don't care. It's compiled, it's there, and it's reusable. It's cacheable. So you've compiled it once, you can re-execute multiple times. You don't have to recompile every time. Runtime is different. And I like to put a dash between run and time, and I will explain why later. But it's what is happening during the execution of the program. Okay? So what happens at runtime is similar to what happens at compile time, but you can do it during the execution of the program. So when we talk about Groovy scripts, often what you don't realize is that when you execute a script, you have a Groovy runtime that is spawned, and then the class is compiled during the execution of the program for scripts, right? And actually, Groovy is smarter than that. You can do the two. You can pre-compile everything. So this is what will happen if you use the command line Groovy C, or if you use the Maven plugin, the Gradle plugin, the Ant plugin, whatever you want. You can pre-compile some classes. And then Groovy has also the ability to do the same during the execution of the program. So you can create classes during the execution of the program. And a simple class that you can create is a script. So there is a consequence for that. The consequence is that when you get the Groovy runtime in your application, you come with the compiler. So if you compare with Java, actually there is something very different in Java. You have two versions of Java when you install Java. You can either choose to install the SDK, the JDK, or you can just download the GRE, Java Runtime environment. And actually, in most of the cases, the only thing that the end user cares about is the GRE. The SDK is for you, developers. Often you just run on the SDK because it's more practical, but you don't need it. With Groovy, you always come with the compiler. You have to know it. So we're trying to improve that and separate the compiler from the runtime, but yeah, for historical reason, it's not that easy. So what is the difference between runtime and runtime? It's interesting to have the difference between the two. For me, a runtime without a dash is something that provides support during the execution of the program. So when you have a Java program, you're using the string class, you're using the date class, you're using integers, etc., etc. And all those classes, they live into a special jar or whatever. In JDK 9, it's not the case anymore, but don't focus on that. You have some support classes, and those are the classes, the collections, etc., that you need to execute the program. And it's the runtime. It's a library, basically. So Groovy comes with the runtime too. We have the JDK. Actually, runtime with the dash is something different. It is something that you need to be able to execute the program. So in Groovy, it's a dynamic language, and a dynamic language must come with a runtime. And this runtime is capable of executing the methods. So in Groovy, the main difference between Java and Groovy is that Groovy has a runtime to be able to execute the code. Just because you have more than just some statically bound method calls. Is that okay? So we have a runtime. Oops. Okay. Next one. So now that we know that, we're going to dig into how we generate those classes, those bytes, from source. So Groovy has what we call different compilation phases. For Groovy, we have 9. For some other languages, there are much more than that. I think Scala has more than 30 phases. Sometimes those phases for us as language designers are enough. Sometimes they're not enough. We would like to have more. There are good reasons for that. It's always complicated, but since the inception of Groovy, basically this hasn't changed much. So I'm going to focus on those in bold, basically. Just the others are not as interesting. So the first really important phase that we're going to talk about is the parsing. I don't like it. It's very hard to push actually. Button. So I'm going to move there. Hope you don't mind. Okay. So one thing that is worth noting is that in Groovy you have a tool that helps you to see actually what the compiler is doing. And it's a tool that maybe you've already used. It's the Groovy console. How many people already use that? Yeah. So maybe you didn't even notice that you have such a tool available. You have in the menu, you have something that says show AST. I'm going to explain what the AST is, but basically this is showing you the internals of the compiler. So the first phase, the parsing. The idea is that you have some text, and you want to have a stream of tokens. So how many people remember from the past classes they had what parsing was? It's basically very simple. It is, you have a stream of text and you want a stream of tokens, but there is no semantic behind that. All you have is a list of tokens. So you would say, okay, this is an identifier, this is a class, this is a string constant, but you don't have any idea of the semantics of that at the moment. It's just really a sequence. It's not a tree, it's a sequence of something. So in the past, we've used several parsers. Guillaume mentioned that this morning, but we had actually 3 different implementations of a parser. And we're actually working on a new one that uses Antelope 4. And it would help us a lot to migrate to that, just because the previous one with Antelope 2 is very hard to maintain. And typically, if we want to support some JDK 8 specific constructs like lambdas, it's much easier to do that on Antelope 4 than so. We'll see when this. Actually, this is someone external from the Groovy committers who's doing that job, so you can also help that. And yeah, if you want to see more in detail what is happening during the parsing, you can take a look at that class, Antelope Parser plugin. What is interesting is that basically during parsing there's not much that you can do. If you know AST transformations, anyone? Yeah, some of you? Okay. So AST transformations, nothing you can do during parsing. It's after. So the next step is actually much more interesting because we have this concrete syntax tree that is the output of the parsing. And now, okay, we know that we are going to produce Groovy code. So we know that in Groovy we have the notion of class. We know that we have the notion of script, etc., method calls. We know that Groovy is a language that has the ability to call methods. We know that it has closures, etc., etc. So we have a lot of syntax aspects that we need to represent. And this is the abstract syntax tree. And this is everything that you need in the compiler to work with. So the abstract syntax tree is really the core of the compiler. Once you have that, you can do whatever you want. You can compile it. You can even interpret an AST. It is possible to do that. It's an abstract syntax tree. It has the complete representation of the program. So yeah, basically the core. If you have questions, you can stop me. The conversion is actually pretty dumb because it doesn't have any knowledge of what is a Java class, of what is the imports, etc. It's really something that from the concrete syntax tree tries to represent that. And we're going in the next phases of compilation to transform that into something that has all the meaning of a Groovy program. So the two categories of AST nodes that you're going to find are actually, again, some historical reason for the two categories of nodes. You have expressions and you have statements. And I think that if Groovy was created today, we would actually only have one category that would be expressions, because everything can be expressed as an expression. So anyone knows the difference between the two? So an expression basically has a value, whereas a statement doesn't. And in modern languages, everything has a value. So imagine that you have if, then else. If, then else is a statement. If is a statement. Because it doesn't return any value. What is the value of if something? And actually, some languages define that the value of the if is the result of the execution of the block inside. So you can return a value for if. You can say def something equals if. And then, yeah, you can assign it. So Groovy doesn't have that. Groovy has the legacy of Java. So in Java, you have the differences between the two. You have statements and you have expressions. So a method called is an expression, a string constant is an expression, etc., etc. So if there is something you have to recall from that session, is that in Groovy, if you want to dig into the compiler, you have to know your AST. And it's hard. It's hard because how can you, as a human, understand what kind of nodes exist and what kind of nodes you can create? You cannot. So again, Groovy is friendly, so you have the Groovy console, and actually since you have the Groovy console, you can print the AST. It's not that hard. You can learn the AST just writing some examples and seeing what the compiler outputs from that AST. So it's pretty easy actually to, and I think Groovy just for that is a fantastic language because it shows you what the compiler is doing, and you can see it. So you can learn the compiler theory just writing Groovy programs. And it's pretty fun. Well, at least for me it was fun. So yeah, a simple example. We have print line, so it's the same code as previously. It's print line, and something. And actually, it's probably a bit small for you in the background, but I'm going to show you. So what the AST for that is a method call expression, this one, and inside you have a method call that is this print line. So you can see that in the AST, actually, this appears. There is an implicit receiver for that method call. It is this dot print line. You don't write it, but actually in the AST it exists. There is always a receiver to a method call. It's an object-oriented program. And actually, object-oriented maybe should be called message-oriented programming. So there is always a receiver for a message. So the message is print line, and the receiver is this.
What for static methods? What's the receiver for static?
It's the class. The class itself, yeah. So we have a constant then, because this is a constant, print line is a constant. So it's represented as a constant, and then you have an argument list, and that argument list consists of a J string. So J string is a first-class citizen in the Groovy AST, and then you can dig into etc., etc. So everything is represented as a tree. That's damn simple. Trees everywhere. That's our job. Okay, so actually, everything that you can see starting from the conversion in Groovy, there is one pattern that is applied everywhere. It's the visitor pattern. So you have a tree, and everything happens using visitors on the tree. So even if we think about type checking, it's implemented using visitors, etc., etc. So it's pretty simple. It's a commonly used pattern. It's not very well implemented in the compiler. It has some limitations, but yeah, for you, probably you don't care. It's our problem that it's badly implemented. Anyway, so if you want to take a look at all the classes, take a look at that package. It's pretty interesting to see all the types of nodes that we have, and one thing that you should know is that if ever you decide tomorrow to write an AST transformation, you will have to deal with that. It's not a public API, but it's effectively public API. You know, the difference that it's in the package, you see it, you use it. Well, so if tomorrow we change it, maybe it's going to break. It's been there for a long time. We've not made any breaking changes in that area for a long time. Maybe it's going to happen for Groovy 3, just because of JDK 9. So, but probably your applications will break before ours. So. Okay, next. So I was talking about that AST that we have after the conversion phase. But it's dumb. And why it's dumb is because it doesn't have any semantic. And what I mean by semantic is that you see string in your source file. How do you know that it's a Java class? How do you know that it's a class? Could be a constant. It could be a method call. Could be something else. We have to do some semantic analysis of the tree to understand that actually, okay, on class path, there is something that happens to be called string. Maybe actually this token is a class reference. So this is what semantic analysis is about. And this is where most of the time spent in compilation is spent mostly in that phase. Just because it's really, really expensive. It has to look at for every token and check if it's a class. And if it's a class, it has to resolve it. And maybe it's not, but it has to do the job, because in the end, you have to know if it's a class or not to be able to compile it to bytecode. So typically, when you add some imports, you will tell the compiler, okay, this is a candidate for a class. Then you have to find it on class path, analyze the methods, etc., etc. So everything is done during the semantic analysis, but it's not all. The other things that we can do typically is analyzing the scope. So when you have an inner class, You don't want the methods of the inner class to be those of the outer class. So there is scoping. But more importantly, if you have a method, you don't want the variables to leak into the other methods. So we have to analyze the scope of variables. Everything is done during semantic analysis. And this is very intensive, very CPU intensive, so slowness happens there. So just to give you an example of how slow and how we can improve that, actually I had a problem, a performance issue in Gradle. And the performance problem was that in Gradle, they're adding a lot of default imports for you. So how many people use Gradle? Yeah, cool. So you've never used a fully qualified name for copy when you create a task of type copy. Just create type copy. And the reason you can do that is that copy is imported by default. And actually there are lots of classes imported by default. And the more classes you have imported by default, the more time it would take to resolve because you have to check everything. And there was a performance problem with that. So I had to implement a custom, what we call a resolver, just to make it faster, just because we have some knowledge of Gradle, so we know which classes can be imported or not. So, and just doing that, I think the compile time to 11 was reduced by half for bigger scripts, so it's really important. Okay. Don't tell me, yeah, okay, I have 20 minutes left. Cool. This word is unpronounceable for me, canonicalization. Okay, I kind of managed to do it. This is not the most important phase, but it is some kind of important for you as AST transformation designer, potentially, because this is often the first phase where you can actually hook and have all that semantic information available. Because before, you don't. So typically, you wouldn't know that a string is a string. Starting from canonicalization, you have it. So it does more than that. It will actually transform the AST to be able to represent the inner classes. We have special code for traits in that phase too. So it's basically finalization of the semantic phase. But this is the first phase that is interesting really for AST transformation designer, because this is where you have an almost complete AST. So you can start working on the AST at that phase. Instruction section is really something interesting because it doesn't say what the name says. It doesn't do what the name says, sorry. So apparently, so I wasn't born when this happened, but apparently before it was used to select the Java target bytecode level. Actually, we don't care about that. It's something that is in the compiler configuration. So while the name remained, not to break the binary compatibility, the semantics of that phase totally changed. So now at that phase, we have the type checking happening. If you use type checked, if you use compile static, this is happening at instruction selection. We have again some traits weaving happening there. Basically, this phase is the last one before we actually generate bytecode. So before, everything we manipulate is just an abstract syntax tree. So we don't manipulate a class, we manipulate a class node. We don't manipulate a method, we manipulate a method node, etc. So it's everything that JVM knows, but abstracted. After that phase, okay, we're going to generate some bytecode. Hard stuff. Actually, generating the bytecode is probably the easiest thing of everything we've done so far. Because at this phase, everything is available. Type checking has been done, so we know exactly which method we should call if it's statically compiled. It's just done bytecode generation, super easy. So what it is to generate bytecode? It is the phase of converting that abstract syntax tree into something that the JVM can load and execute. And the JVM requires JVM bytecode. So to do that, we're not generating bytes the hard way using write byte. No. Hopefully there are some tools to help the poor developers that we have. And we use ASM for that. It's probably the most widely used bytecode generation library and probably the only one that is up to date. So there are always new releases of ASM for each JVM because there are new bytecodes available. Typically in Java 7 there was invoke dynamic added. In Java 9 they're going to add a new type of method handle, which is called the var handle. It requires changes to bytecode, etc., etc. So there are things happening, so you have to be aware of that. We'll come back to it. After the bytecode generation, what we have is an optional phase that is called output. And this one is super easy. Take the bytecode, write it to a file. And obviously, it's optional because if you generate a class at runtime, you don't necessarily want to have a concrete file on the file system. You can just load it from direct the bytecode that you have generated in memory. So totally optional phase. Last one is called finalization. And this one does nothing. So that's pretty funny because we only have 9 phases. And there are actually 2 or 3 that are really intensive and super intensive. We have so many things to do inside. And sometimes when you write HT transformations, it's a problem because you want to be between the 2 and there's nothing. So, oh, shit. And then in the end, you have a phase that does nothing. How cool is that? Yeah. We have a phase that does nothing. So effectively, we have only 8 phases. And the problem is that adding new phases is potentially breaking changes. So we're kind of stuck. So that's cool, because I just explained to you how you can from a script to a class that is loadable by the JVM. Actually, it's not that true, because it's more complex than that. When I have a script, I can have multiple classes into the script. I can compile multiple files together, and they should be represented. We have the notion of a unit of compile. So when you compile something, actually, we need something that represents what we're going to compile and the different phases of the compilation. So we're going to compile a script, and then going through the phases. So for the bravest of you, you can actually take that class, compile unit, and do all the compile phase, trigger all the compile phase one by one just using that class. It is the orchestrator of the compilation, basically. And what it processes is a source unit, and the source unit represents the source. And actually, we can have different kind of sources. We have files, we can have strings in memory, you can have remote files. Well, it's a source unit, so something that abstracts what you're going to compile. Yeah, and what it would produce in the end is a compile unit, and in a compile unit you would get the AST. This is where you would get the AST, from the compile unit. Anyway, not the funniest part. Come on. So AST transformations. So when you do AST transformations, what you're doing actually is hooking into the compiler. So Groovy is one of the languages that lets you hook into the compiler and do whatever you want with the AST. AST transformation is that. So when you use the toString annotation, it is an AST transformation, and it is something that is in the code and that will transform the AST. That's That's why it's called an AST transformation. It's code generating code. And we don't generate a string, we generate an AST, so we transform the AST. So an AST transformation works at different phases. At best, it can run at the conversion phase, so right after having been parsed, because before, obviously, there's no AST, so what you want to transform is you have nothing to transform. Most of them will run at semantic analysis just because this is the first phase where you will have the semantic done. And usually you don't do that after canonicalization, just because after that, it's what? Who followed? Oh, guess. Oh, shit, I'm cool. So, instruction selection, so type checking. So to do the type checking, you have to have the complete AST. Actually, for different things like the markup template engine, if you know about it, it is doing something after that. So after the type checking. Because it's using the type checking extensions and it's transforming the AST after the type checking. So it's doable. It's doable, but it's very hard because you have no nets. Basically, everything that you produce, everything that was done by the compiler for you during semantic analysis, you have to do it yourself. Okay. So when I'm talking about user code, I mean that AST transformations are not, in general, bundled into the Groovy distribution. So what you have is toString, is tuple constructor, it's compile static, everything that Groovy has implemented as AST transformation is supported by us. But you, as a user, you can also write AST transformation. If you do that, well, again, who knows what happens. So actually, it was interesting for the Groovy team to leverage the same techniques that you would use as a user to write your programs inside the compiler itself. Because we have the structure now. We have AST transformations to do that. So traits were implemented as AST transformations. Type checking was implemented that way. And one of the reasons is that we don't want to add more ad hoc constructs just to support type checking. We want to use the same APIs as you would. Because if we break something, it's more likely that we were breaking something for you too. So yeah, it's just something that you have to be aware of. So stamped type checking is implemented at that. And what it does is mostly doing some annotations on the AST node. So imagine that you have a method call, well, foo.bar, no arguments, etc. How do you know that foo is a string? Well, because you have done some analysis before. Flow typing, typically. So foo maybe is a variable that has been defined and it references an argument from the method call, from the method parameters, so we can know that it's actually, okay, it's the same type. So we're going to annotate every variable in the code with the type. So it's just, yeah. It seems to be simple, it's not that easy. And it's very buggy, especially when it comes to generics. But yeah, maybe you face such problems. So it's just interesting to know that it's implemented as an AST transformation, so it's really powerful to have access to the AST for you as a user. So yeah, I didn't want to finish that presentation without actually showing some bytecode, because everybody loves to see some bytecode. So Groovy targets the JVM, but you know that since Groovy 2.4, we actually also run on Android. Android has a different bytecode, and we don't do anything different than what the Google team is doing, typically. So we don't have a specific generator for Android. It takes the classes that Groovy generates and converts them into the Dalvik bytecode. So we don't do anything special. We didn't have to do anything special for that. So it's the same library for the two. But actually, when we generate the bytecode for Groovy, we have 3 different backends. One is what we call the legacy backend. That is the good old call side caching. Maybe you know the name or not. If you ever have seen an error with a call side in the stack trace, that's it. Then we have a different backend, which is the invoke dynamic one, which is supported since JDK 7. And it's supposed to be faster. It's not on JDK 7, it is on JDK 8. And the last one is static compilation, and actually we generate that. We generate different bytecode depending on the case, you're dynamic, you're static, you're using Java 7, etc., etc. So lots of things. So I'm not going to explain all the things that you have there, because in 45 minutes it's not doable. What is more interesting is see the difference between the 3 backends. So for that simple method, I'm going to show you the bytecode that is generated for that, using the legacy bytecode. And it's pretty simple, actually, right? So we have a get call site array, we have a call site call. Okay, where is my code? Well, I don't get it. Actually, the old call site caching is just unreadable. You can't debug that bytecode. It's not human possible, right? But it works. Then we have the invoke dynamic method. And the invoke dynamic is a new bytecode instruction that was added in JDK, and that supports dynamic languages and dynamic invocations. And actually, it's also used by the Java itself in Java 8 for lambdas. But it wasn't by the time we started that work. And actually, the bytecode starts to be much shorter, and you see the invoke dynamic instruction that is just saying, okay, I'm going to invoke a method dynamically, and this is the reference of the method that you're going to call. So you have some descriptors that you can put. And the last one is when you just use the static compiler. It's damn simple. Invoke static, just a method, everything is wired, done. So different bytecodes for different runtimes. And this is Groovy, isn't it? Especially when you think of mixed compilation, where you can have in the same class dynamic and static code. Well, I think I'm out of time. I just wanted to show the bytecode AST transformation, but I don't have time for that. It's super fun to try. It's an AST transformation that lets you write bytecode directly as a method body, and it generates bytecode directly. So it's pretty nice to learn about Java in bytecode. And I'm out of time, so no class loading, no root loader, no classroom. Questions?
In the joint compiler, where does the Java code or bytecode come in?
So the joint compiler is an interesting topic just because it is in the middle. So the idea of the joint compiler is to generate some Java sources from the Groovy AST. And then we generate that during the compilation, and we can compile the Java classes and then go back to the Groovy compiler to be able to complete everything. So it happens in the middle, and it's causing some troubles. If you've ever used some AST transformations, sometimes you would see that actually Java doesn't see the methods that the AST transformation is doing, just because the stubs. So the Java sources have been generated before that. So it's limitations, but it's going to change. I think Jochen plans to do something in GreatConf about a new joint compiler for Groovy. Yes?
Yeah. One thing, you said traits are an AST transformation, no?
Yes.
But I mean, you'd have to change the syntax of the language. You had to add the trait keyword, no?
Yeah.
You can do that. I mean, like, there is any way you can hook?
No. So the initial implementation of traits was using the @trait annotation on an interface. And then we discussed that and said, okay, this is such a critical feature that we want a new keyword for that. So this is the first keyword that was added, I think, since the beginning of the language.
Yeah, I would like to continue with the trade topic. If the AST, I mean, if you are adding to your class some trade, it is like implementing an interface. So I don't know if in the AST is like saying that you are going to implement that interface and that other interface. Yeah, only that matters is that you hook into your compiler previous that the AST trade transformation starts. Is that correct?
Yeah, so if you're really interested in that topic, actually I gave in the long version, the 1.5 version, I explain exactly what the traits transformation do, because there are actually 2 transformations for traits that run at 2 different phases, and it's combined to do something, and yeah, it converts the trait into an interface plus helper classes, etc., etc. So there is a long version of those slides with the explanation of how it works. So, okay. I think we're running out of time, so thank you. Enjoy the rest of the conference.